So now let's talk about the ripple carry and then the look ahead carry adders. So what is the ripple carry adder? So imagine you have this kind of the adder. So this is a 4-bit parallel adder. So this adder here, you can see we have the 4 full adders, right? And we have the 2 input sequences A and B, and each has a 4-bit length. So A is 4 bits. So in this case, let me change my pen. Okay, so A is here the 1, 1, 1, 1, right? And the B is a 1, 0, 0, 0. So we're adding these two sequences together, right? So again, the A is 1, 1, 1, 1, and B is a 1, 0, 0, 0. Now, when we add these numbers together, what we do is we start from the rightmost bit, right? So we always start from the rightmost bit. So first we perform this addition, 1 plus 0, right? Okay, so 1 plus 0 is equal to 1. And then only we can proceed to the next bit. So we do again the 1 plus 0, we get 1. And then we can proceed to the next bit. And then 1 plus 0 is equal to 1. And then we proceed to the last leftmost bit. In this case, 1 plus 1 is equal to 1, 0. Okay, now what is the drawback of this adder? The problem is each next bit have to wait the result of the previous addition. Why? Because we have to wait for the carry bit, right? So if you look, for example, here the adder implementation, so whenever you do the A plus B, right? So this is A0 and B0, so A0 and B0. Whenever you add these two numbers together, the next adder here, so this adder here, so let me change the color to make it easier to see. So this adder here, right? So have to wait for the result of the previous adder. So in this case, why? Because one of the inputs are connected to the output of the previous adder, right? So this adder have to wait the result of this addition. And then this next adder have to wait the result of the previous adder. And then the last adder here have to wait the result of the previous adder. Okay, so I hope this is clear. So whenever you do the addition, whenever you use this 4-bit adder, so let me change the sequence. Okay, so this is the implementation in Circuitverse. So we have the 4 full adders, right? So we have the 4 full adders, and this is the rightmost bit. So in this case, A is equal to 1, 1, 0, 1, and B is equal to 1, 1, 1, 1, for example. So now, when you want to add for example, A0 to B0, right? So, and then A1 to B1, the output of this adder, so A1, B1, have to wait for the output of the A0 plus B0. Why? Because in this case, when you do the A0 equal to 1 plus 1, the carry will be generated. So this is the carry. And this carry is going as an input to the next full adder. So this is the drawback of this full bit adder. Why? Because you have to wait, each next bit have to wait for the previous bit, result of the previous addition. Each next addition have to wait for the result of the previous addition, and this is the drawback. Why? Because if it takes, for example, let's say if it takes the 8 nanoseconds to add the single bit, then to add the 4 bits together, you have to wait for 32 nanoseconds, right? So because each bit have to wait for the previous one, and you have to multiply it by 4. So in this case, this adder works very slowly, right? So 8 nanoseconds for the first bit, and then another 8 nanoseconds for the next bit, etc. But can we speed up this process? So this effect is called the ripple carry adder. So in ripple carry adder, each full adder have to wait for the result of the previous full adder. Now, can we speed up this process? Yes, by using the look ahead carry. So what is look ahead carry is that we can predict the carry. If the carry bit will be generated or not, we can predict that. How we can predict? So let's look at our full adder. So this is a full adder. So this is the full adder that we have here, right? Now, by looking at the full adder, we know that, okay, so when the carry is generated, whenever A is equal to 1 and B is equal to 1, we know that carry will be generated. So this is the one case. Another case, the carry is generated when the A or B is equal to 1 and also the input carry is equal to 1. So right here, so for example, A is 1, input carry is 1, of course there will be the output carry. Okay, So this effect, when you have the A is equal to 1 and B is equal to 1, this one is called the generated carry. So in this case, the carry, output carry will be generated. So this is called the generated carry. Another case when the A is equal to 1 or B is equal to 1 and input carry is equal to 1. So in this case, we again have the output carry here. This one is called the propagated carry. Why? Because this carry is the propagated from the input to the output. So this is called the propagated carry. So now we know that just by looking at the inputs here, so just by looking at the input values, right? Just by looking at the input values here, we can already predict if there will be the carry generated or not, right? So just by looking at this, we can predict if the carry will be generated or not. So meaning we can use this knowledge to create a better circuit, right? So the carry is generated, again, as we said, the carry is generated when the A is equal to 1 and B is equal to 1. So in this case, this is called the generated carry, right? So